The first challenge I did from this competition was a secure file system, which we exploited with a hash length extension attack. And then we also solved this other crypto challenge, Key Server, which was about breaking RSA signatures. So let's continue the path and do the last crypto challenge. I wonder what we will have to break this time. Crypto 150 points. Secure File System version 1.92r1. That version number is already suspicious, but let's read the description first. After the horrible debacle of the first file system, we got together again, invited our friend Mr. Vodka and waterproofed the secure file system. You can test it again, but this time it uses unbreakable encryption. The file system allows you to request the contents of one or more available files by using the following format, which is basically the same like in the previous file system challenge. Token, then a hash symbol, followed by one or multiple file names. And we get a list of example tokens and file names. Here's how it looks like when you run the challenge. You get the list of files, and if you supply the correct token and file name, you get the content back. And somehow we want to read pass WD. Before I tell you the solution, let me explain my thought process here, because I went into a complete wrong direction at first and somebody on IRC had to nudge me into the correct direction. I completely failed this challenge. So first I had a look at the version number. That seemed too specific to not be a hint. And it could have led me to the correct solution right away, but I got distracted by the list of examples. Because there we can immediately notice that the first part of it is always the same, which I interpreted to be some kind of block cipher, and I thought the first block always encrypted the same secret key or something, similarly how the bad hash implementation prepended a secret key in the first level. And the version number for me became the bit length of the cipher. The text said it's a strong encryption, so I went to look for ciphers with 192-bit options. I mostly looked into AES, but all attempts of manipulating blocks, for example for padding Oracle, didn't work. Another lead I had was a waterproof file system. I figured maybe it's some kind of whirlpool hash, but that also didn't make much sense. Then maybe it had to do with vodka? Maybe there's a Russian cryptographer named Gorbachev with some weird obscure encryption? But everything I tried just didn't seem to be the right path. I kept running in circles and really wanted to give up. Then I got a slight hint to focus more on the version number again. And while I did find hints to elliptic curve cryptography when googling for the version number before, I ignored them. That was a mistake. It turns out 192r1 is a curve parameter for ECDSA, Elliptic Curve Digital Signature Algorithm. Okay, so I know this elliptic curve stuff exists, but I never really looked into it as much as I should have. While RSA seems pretty straightforward, this stuff always seemed a lot more difficult to understand, so I started to read Wikipedia. And there's even a section called Security, where they say that Sony didn't properly implement the algorithm on their PlayStation 3 because one of the variables, K, was static instead of random, and apparently it means you can break the signature. So let's have a quick look at the algorithm and math itself. So the private key is an integer randomly selected, and the public key is the result of some fancy elliptic curve multiplication. You hash the message you want to sign, like with RSA, and then you have to select a random key, and it must be securely random. Then you calculate a point on the curve based on that number. Then you do some more calculations and you get R and S, and the signature is the pair of R and S. So when we look at our example tokens, we can assume that those are the two different values, R and S. And R is always the same, which is suspicious. If you look what R is, then R is basically X, and X is the X coordinate of the point on the curve after the elliptic curve multiplication with the secure random K. This means for every signature, the multiplication had the same result, which means K was probably the same. Boom, that's it. As a standard notes, it is crucial to select different K for different signatures. Otherwise, the equation in step 6 can be solved for the private key D. Given two signatures, RS and RS prime, employing the same unknown k for different known messages, an attacker can calculate some fancy stuff and recover k, and then you can solve this equation for the private key d. Done. I'm not very good in math, but I knew that this is such a basic security issue that I'm sure this came up in some CTF competitions before, and surely somebody implemented this calculation in Python already. That is generally a good hint for CTFs. So I googled specifically for CTF challenges with ECDSA, and sure enough, I find some example code. I can just copy that code, but I also wanted to understand what it does. So let's do it step by step. Let's start by getting ECDSA Python module, because we might reuse some functions, and in the end I use it to create a proper signature for the file name we want. Let's copy two of the example tokens and messages and extract the values. So we got R and S from the first message and R and S from the second message. Then I try to follow the Wikipedia article. So first we check the two R and S if those two signatures are vulnerable. Then I want to prepare most of the values as I need them. First I hash the message we want to sign and convert it to a number, so we can do calculations with it, which is Z1 and Z2. Then we need N. N is the order of the curve, so we can get that value from the module. To find that, I just look around in the source code of the ECDSA module. Next we're gonna recover K, like it says here on Wikipedia. The first part is simply Z1 minus Z2. So this is basically just the hash of message 1 minus message 2, divided by the subtraction of the signature. And because you all got some basic math education, you know that instead of division, you can also multiply the inverse. Like 6 divided by 3 is the same as 6 times 1/3. So we just multiply the inverse of S1 minus S2. And we can reuse the inverse modulo function from the ECDSA module. Everything happens here always modulo the n. Okay, now we got the k. So next we recover the private key DA, which is super simple. It's just a signature times k minus the hash divided by r. And there we have it. K and the private key recovered. Now we just have to figure out how to plug this into Python ECDSA to sign a value for us. Again, I just look at the source code of the module, find the correct classes, and to test this I'm gonna assign a message which we know the signature of, and print the original and the calculated signature. This looks perfect. Now let's sign pass WD so we can get the flag. Copy the signature, send it to the board, and we get the flag.